Okay, so let's make a start. Okay, so we got up to here in the last lecture. So now we're going to look at some examples, okay, of modelling and electronic systems, so that just so we can put things in context. Okay, so as I said, in these first couple of lectures, not much mathematical stuff. It's all just trying to set the scene a bit. Okay, so perhaps we could look at something like an RF transmitter. Okay, so we have a modulator, okay, and we have a coaxial cable that connects the output of the modulator to an RF amplifier. Okay, so the coaxial cable, we model that with a 2-port. We'll see later how we do that. The RF amplifier, we also model that. Could also be modelled by a 2-port as well, okay? 2-port. And then that's connected to another coaxial cable, which, as I said before, isn't a lump circuit element, but again we have a circuit theory model which is a 2-port, and then we have an antenna which we model with a 1-port, okay? And that also is not a lumped element, okay? So how large do you think an antenna would be compared to the wavelength of the transmitted radiation? What's typical values? Is it small or is it large or comparable to anyone? That's right. It's typically like a quarter or a half wavelength. So these are sort of values of. So it's quite large compared to the wavelength. Okay, it can't be represented as a lumped element. Okay, so but we can make a model for it. Okay, and that's the key thing. When we make a model for it, we've got a VI relationship at this port. Okay, something that for every voltage it tells us what the current's going to be. Okay, then we can use that model in circuit theory, even though the actual element doesn't meet any of the criteria for circuit theory. Okay, but we have a model. Another system here, we've got, perhaps on the other side, we've got the receiver. Again, we have this antenna, which is, again, a large element which is modelled by a 1-port. We have the coax. We also have the receiver, could be modelled by a 2-port. And then we have something on the other side, the speaker, to convert the electrical energy into sound energy, okay? So again here, this could be modelled by a 1-port, okay? But, it's not just a pure electrical system with small elements, okay? Actually not that large, actually probably compared to the frequencies, the acoustic frequencies, it is fairly small, but it's also got a lot of mechanical and magnets and stuff like that. Okay, so we have to develop a model for that we can use in circuit theory, so that we can predict how things are going to work. Okay, so looking at perhaps the RF amplifier component. Okay, so you can see here it's got a number of components. It's got inductors and capacitors and a transistor. Okay, it's also got these little square bits. So does anyone know, has anyone done high frequency electronics before at all? Does anyone know what those little sort of rectangular pieces represent? Okay, they're transmission lines, okay? Little bits of transmission line, okay? So when you actually make a printed circuit board, you often have one part of one plane of the board is ground, okay? And on the top of that you have wire traces. And the wire traces with respect to the ground make a transmission line, okay? And in these high frequency RF circuits, you can use sections of different size transmission line or different size traces to produce transmission lines of different characteristic impedances, okay, and with different lengths. And in fact, they can act as transformers, okay. So, you know, that they can act as a bit like an inductor or capacitor or something in between, okay. And you may remember last year, if you did, any of you do 3021 with me last year? No? Okay, well, you did. In 3021, one of the things we talked about was these lossless circuits of inductors and capacitors that can effectively transform the impedance from one input port to the other port, and then they look different. Okay, so we were mentioning that indeed that's what they do for a lot of RF amplifiers and things like that, you know, to match the output of the transistor impedance, output impedance of the transistor to that of perhaps the coax. Okay, and that's exactly what's happening here. Okay, so these bits of transmission line act as a transformer to transform what the impedance seen looking in is matched to the output impedance of the particular transistor, and the impedance looking in this direction isn't matched to the impedance of the coax, and at that particular frequency it's lossless. Okay, so that's, and perhaps, you know, the printed circuit board for that particular circuit looks something like that. Okay, and so you've got these different sections of printed circuit board traces on the top plane that have different widths to form these transformers. We'll look a bit more about transmission lines and how they can look as capacitors and inductors in the future. Okay, but they're all not small elements. Okay, so you know, that's not a small element, this is not a small element, these are not small elements, okay, compared to the wavelength. So again, we need to have models to use them in circuit theory, okay?
What do you mean by transmission line? Because what I gather is like high voltage line.
Yeah, but that's true, and that is a type of transmission line in the sense. Okay, so that's a power transmission line, okay? And that main purpose of that is to transmit power from one point to another, okay? But here, okay, that is also fits in with the theory that we have developed here, okay? Because even though the power transmission's at 50 hertz, which is a low frequency, the actual size of the transmission lines is very large. That's a good question, right? So also the theory here applies to those. But more generally here, we're talking about transmission lines which take signals from one point to another. Okay, so for instance, this cable here is probably a twisted pair with a shield around it, okay? And that's the transmission line. Okay, because, you know, there's an electric field between, there's probably a number of pairs, okay, but between each pair there's a signal being transmitted, okay? So that at one end there's a high-speed signal that's launched into that line, okay, and it propagates with delay down that line, okay, and the delay through that line is probably a lot larger than, you know, the rise and fall times and the periods of the signal going down, okay? So you can't consider it as a short circuit anymore, okay? You have to have some special model for it, okay? That's a transmission, or a coaxial cable, or these sort of cables as well, because this is high frequency stuff, right? It's got a lot of information coming out. They're very fast. It's got to go some meters. So that's a transmission line, okay? The antenna, okay, so you know, to actually understand how it works in electromagnetic theory, okay, but you could you could make a model from the results of electromagnetic theory, which will consist of circuit elements like an R, an L, and a C that represents accurately the VI characteristics at this port for certain frequencies or over the range of frequencies you're interested in. Okay, so you can make a model. Okay, but also there's a context to when you want to make a model. Okay, so for the antenna, you need a model when you want to design the circuit because you want to deliver perhaps the maximum power from the amplifier or the coax to that antenna at that particular frequency. So you need to match the impedances and all this sort of stuff. Okay, so that's one context. The other context, so it's the VI characteristics associated with the port of the element. Okay, but there's another context for modelling the antenna. You might want to model how it emits radiation. Okay, so then you're looking at the radiation pattern. Okay, which so you need a model for the antenna in another sense that models how radiation is emitted in certain directions. Okay, so again, we should always think of models in what they're being used for. Okay, so here's an example of another electronic system. So it's a capacitor, okay, a high frequency capacitor. Okay, so current travels through wires. Okay, so but when a current travels through a wire, it sets up a magnetic field. Okay, and that magnetic field generally can resist the flow of current, so it forms an inductor. Okay, and at high frequencies, obviously inductors impede the flow of current. And the capacitor designed for high frequency systems, what they tend to do is have lots of plates in parallel with each other, so that all these inductances that are associated with these leads are in parallel, so the overall inductance goes down. Okay, so at low frequencies, okay, we can model this just as a pure capacitor. Okay, that just a C. Okay, but as frequencies increase, okay, we may need to make a model that's more complex. Okay, that doesn't have to capture everything, but captures the main characteristics. Okay, and that we can use in our circuit theory simulators to actually predict how systems are going to work. Okay, so the actual component might have a response that looks like this. So here we've got the frequency on the bottom, and we've got the magnitude of the impedance looking in. Okay, so we can see at low frequencies the impedance decreases linearly with an increase in frequency. Okay, so is that correct? Is that what a capacitor should look like? Anyone? What's the impedance for a capacitor as a function of frequency? J omega C, right? So it should be, this is a log plot, so it should look like a straight line, right? Because it's 1 on J omega C, right? So it's good. But then it gets to a point where it gets to a minimum, which is pretty low, but then it starts increasing again. Okay, and what is the component that increases with impedance with frequency? It's an inductor, right? So it's J omega L. Okay, so at this higher frequencies, the inductance starts to become significant. Okay, and so a circuit model for that using ideal lumped elements, so it could be an ideal capacitor in series with an ideal inductor, and also some ideal resistance, which would model, the ohmic resistance of the leads. So, that's an example of, modeling creating a model for a real component that you can use in circuit theory, okay? We'll use those models. When you do the second half of the course, you'll do this project on power distribution in electronic systems, okay, which is a really good project, to be honest. You know, if you design anything in electronics, you're going to have, you know, integrated circuits and all that sort of stuff, and you're going to distribute power to them, okay? And so you have to design always a way to distribute the power consistently and without noise and all these other things, right? So you learn about that in this project, okay? And so, you know, the actual system consists of, you know, a power supply that produces a regulated voltage and goes through these traces to the various components, okay, and they're on different sections which might have these power planes, where underneath you've got the ground plane, and on top you've got this plane which carries the 5 volts or whatever it is, okay. And so, you know, at different frequencies, the response, if you're looking in at, you know, looking to one of them, so this is a multi-port system, right? So you have perhaps the power supply, regular power goes in at one port, and then at all these little ICs, you also have another little port that's tapping off the 5 volts with respect to ground, right? So you have a little ground pin and also the VCC pin, and also here where you've got these capacitors and all that to help smooth out all the power supply resonances and all that, you also have ports, okay? So it's a multi-port system. But anyway, you know, if we're looking in at one of these ports and seeing what the impedance looks like, then you end up with a lot of these resonances, okay? And later, when you do the project, you understand those resonances come from, you know, the interaction of the different inductances and capacitors in the actual system, which come from, you know, the physical structure of, you know, the printed circuit board and the lines and other things as well, okay? And even at high frequencies in the printed circuit board, you also see these really sharp high frequency resonances, and they're due to electromagnetic modes on the actual power planes, okay? So, you know, electromagnetic waves can bounce back and forth like, you know, like modes on a string, right? So you also get high frequency modes, okay, so on these things. So there's a whole range of things you need to consider and model. Okay, so you've got to model large structures, especially at this end. These are very large compared to the signal wavelength. If you're working at these very high frequencies, then, you know, you need models for them to be able to predict what's going to happen. Now, there's also small elements like capacitors, and, you know, we'll see that indeed if you have the correct models, you can use circuit theory to, you know, predict and design such systems, okay? And then you need both circuit theory and EMT. So EMT gives you the models that you can use in circuit theory, okay? Another interesting thing related to the power supply is a DC regulator, okay? So, you know, if you have a power supply which is just a battery, okay, connected up to your whatever it is, then, you know, perhaps you'd model that with an ideal source which the potential difference is and outputs is related to, you know, the chemical reactions in the actual battery, okay? and you might have some resistance, okay, for the leads and plates and everything. But in most cases, like for this computer where we connect it up to the mains, you often have a voltage regulator, okay, which takes, so from the 240 volts you might have a transformer that steps down to something in 10 or 5 or 15 volts or something like that, and that gets rectified, and you have some noisy and uncertain, unregulated DC-like voltage coming in, and you want to produce a well-controlled, regulated DC voltage out, okay? So a way to do that is to have some electronic circuit. And in fact, in the exercises online, there is this circuit, and it does go through how you can find the response of such a circuit, okay? So the idea of a power supply is really to deliver a constant potential difference at very low impedance, okay? So whenever you take current out of that supply, you don't cause very much of a drop in the voltage output, okay? That's the ideal. The ideal voltage source has zero output impedance, okay? So, if you take any current out, it's not going to change the voltage, okay? So we want to try and, in the regulated DC supply, you want to try and replicate that, okay? And the way these regulated circuits work is that they take the unregulated input and they have some voltage reference system that maintains a very, very precise voltage, okay? And then they use that as a reference, and they look at what the output voltage is, okay? And they use feedback and comparing that feedback signal to what the reference is, they adjust the amount of current flowing at the output, okay? Okay, so with that sort of feedback system, at low frequencies, they can get very, very low output impedance, okay? So if you need more current, you start pulling it, and they'll sense that, well, there's a bit of a drop in the output voltage, so we'll use the feedback and control this transistor to give you more current, okay? So in that sense, at low frequencies, they can get very, very low impedance, but it doesn't stay like that at all frequency. So you can see at higher frequency that increases. So why would that be? Why would at higher frequencies the output impedance of the DC regulator increases? Anyone got any ideas? It's due to the bandwidth, okay? So these amplifiers and the circuit has time constants involved with capacitances and other reasons, okay? So it can't respond so quickly to higher frequency signals, right? So it's due to limited bandwidth of which this feedback system works, okay? So at high frequencies, it just simply can't respond as well as at low frequencies. So, and if you had, so it's a log-log scale, and you have basically the impedance increasing in a straight line, what could you model that system with in terms of bulk lump components? What would be a good model for that regulator system, okay? So, when we come to look at the system in its entirety, you wouldn't really want to have to model all the complexities there, but what would be a simple model of a couple of lumped elements that would represent reasonably well that particular characteristic. Anyone?
You mean like an RL circuit?
It'd be an RL circuit, right? So it'd be a resistance here to represent the low frequency, then an inductor in series, okay, would represent that, would be a good model for that particular regulated circuit, okay. So, and in fact, that's what you see in the project. You'll see that, you know, the model for the regulated power supply is a resistor and an inductor, plus an ideal supply, right? Okay. Okay, another one we're saying is the speaker. Okay, so, you know, there are electrical components in the speaker. It's got a coil, okay, but so it's going to have inductance, it's going to have resistance, okay, but, you know, it's also got, you know, these diaphragm which is moving, okay, so mechanical components and magnets and stuff like that, okay. So, you know, but using EMT and laws of motion, you could construct, you know, a mechanical, you know, like electrical equivalent to the mechanical elements, okay. So, you know, these capacitances, resistors, and inductors don't exist really, okay, but then based on, you know, the mathematical models for this, they if you include them in the actual circuit for the actual speaker, then at the correct frequencies, the VI relationships at this port will represent quite well the VI relationship at the real device, okay? Okay, so then you can use this with circuit theory to actually predict, you know how well your system's going to work, okay? So how well you're going to deliver energy to, you know, sound waves, etc. So, you know, so here we've constructed a model that we can use with circuit theory, even though this element has other things besides circuits in it, okay? Okay, so another thing so related to also the project, and also modelling. Okay, so that's probably the root cause of why we do modelling. So on power planes as well, as I was saying, in a power supply system, you want to supply power to, you know, these devices, and especially if they're digital integrated circuits. What will happen is that as logic levels switch, okay, they will have to charge or discharge capacitances or drive transmission lines, okay. So you often get very strong current being drawn from the power supply in very, very small amounts of time, okay. So if the actual power supply system is not designed properly, then the localized voltage around those pins can drop quite significantly, okay? And that can propagate, well, it can also cause a problem for the device itself. It can cause a problem for other devices around it due to the power supply, but it can also propagate as noise around the plane, okay? And generally, when you transmit signals from one point to another, it's not just one wire, it's a potential difference with respect to a reference, okay? So generally, the actual signals are some voltage with respect to a reference, which is typically the ground plane. And if there's noise on that reference line, then that will also may cause that the actual signals are interpreted incorrectly, okay, and may cause the system to fail, okay? So noise is often a significant issue in designing particularly high-speed systems, okay? Okay, but to actually understand what's happening and to have models where we can show what's happening and we can predict what's happening and we can take actions to avoid, you know, undesired results, we need a mathematical model, okay, of that system, how it's working. Okay, so in this case, we'd be interested in the transimpedance between one particular port on the circuit board and another port. So it tells us the voltage produced at port M due to someone drawing current at port M, okay? So the amount of disturbance that chip's going to cause, okay? And then we can do something about it, okay? So, that's why we need to make models. Okay? Another reason why we need to make models is, you know, to understand what's happening in a quantitative way, okay? And you'll have this problem when you do the project, okay?
What is transimpedance?
So you remember last year we looked at 2 ports and network functions. Okay, so you should look at the 3021 notes. Okay, so you know, the impedance looking in is the relationship between the current and the voltage at one port, right? Okay, but if you have a 2-port, okay, then you're looking, if transimpedance would be the cells, the voltage produced at relationship to the voltage at one port to the current at another port, right? Okay. So transimpedance rather than just impedance, because it's between 2 ports. Okay. So, you know, as I said, if you have 2 ports, then a 2-port system or multi-port system, then, you know, you could do something at one port by drawing current or putting a voltage, and that may affect the voltage or the current seen at another port. Okay, so then you get transimpedance or transconductance. Okay, is that clear? Okay. You can look at the online. I've got the notes from 3021. And I think we talk about network functions, right? Which is a relationship between, you know, voltage and currents in networks, and I'm pretty sure it's there. Okay, so ferrite beads, another example of a model of a component. So this is something you also use in the in the project. So, you know, we don't want to use in engineering or science just vague statements of what things do. Okay, so engineering science, you need to have a mathematical model of something. Okay, so you can make precise predictions, okay, and precise statements about what happens, or, you know, what you're seeing, or explaining what's going to happen. And in engineering, you generally want to design something to either enhance or avoid some phenomena. Okay. Okay, so we don't know what these really mean. We need some model for the system. Okay. So we need a model for the noise source, a model for the victim, and a model for the ferrite bead. Okay, so actual model for a real ferrite bead might look something like this. Okay, so, you know, the manufacturer will give you a plot of the impedance versus the frequency. Okay, it may look, you know, Z may look something like this. Okay, and then extracting from that a lump circuit element of ideal circuit elements that could represent that is given by something like this. Okay. So also in the project you'll use these models for, you know, a real ferrite bead. Okay. So another, as I mentioned earlier, another aspect is modelling these high frequency resonances that occur on printed circuit boards in the project. Okay, so to do that, you know, as I said, it's actual electromagnetic waves reflecting back and forth from, you know, the terminations of the actual power and ground planes, okay? Okay, so actual, the electromagnetic radiation sees different impedance when it comes to the end of the actual plane, so it gets reflected back. Talk more about that later. But that forms these resonances, okay? So in EMT, we can get models for, you know, rectangular sections of plane, ground plane, and when the ground plane and the actual power plane sitting on top of each other, okay? But for other shapes, it's very difficult to get an analytical result, okay? So for these sort of rectangular sections, you can get analytical results from EMT, which, you know, predict all these resonances, but for other shapes, you can't. So how would you think about getting some more complex shape, which looks like an L? What would you think you could do to use the analytical models that you have to model something more complex? Anyone? Yep. That's right. You can stick them, cut them up and stick them together. Okay, so and that's what you'll do in the project as well. Okay, so you can cut it up into rectangular sections and then stitch them together. Okay. And so this is an example of, you know, using multi-ports. Okay. And in fact, so if we have a multi-port model for this particular section of transmission line, which captures all these high-frequency resonances, and another multi-port model for this piece of power planes, which captures all the high-frequency resonances, we can connect them together, okay, and get. In fact, it does this in the. We won't do it in the course, but it's in the book if you want to see, using, you know, matrices. You can get an overall model which you don't have to see what happens in here, okay? So an overall multi-port model for the L, where you've effectively, you know, buried these internal connections, okay? So it goes, if you really want to look at that, that's in the notes. But anyway, you will do exactly this in the project as well, okay? So another thing that needs to be modelled, another example. So these are all examples of where we're doing modelling, okay? Is a via. So on a printed circuit board, typically you might have a ground plane, which is 0 volts, which is, you know, one side of the supply, but also generally the reference voltage for the signals. And you also have the power supply plane, VCC, right? And then to connect the integrated circuit to its power supply or to other signals, you might have a via, something that's like a via is like a little hole. I should bring in a printed circuit board. A little hole in the printed circuit board that's got, you know, a little bit of wire plated around the sides, okay? And it can go from the top to the bottom of the board and connect things in between as well. Okay, so connect traces from the top to the bottom, or perhaps traces in the middle to the top. Okay, so there's a wire that's connecting VCC to the actual pin of the chip. So that also needs a model. Okay, so at low frequencies, of course, it's just like a short circuit. Okay, it's just a wire, maybe with some resistance, but not a great deal. But at high frequencies, we need a model. Okay, because, you know, it's not going to act like we saw for the capacitor and the inductor. They're not, you know, at high frequencies it's a bit more complex, okay, because they're not ideal anymore. Okay, so a model for the via looks something like this. So it's fairly complex model with capacitances and inductances and resistance. Okay. So this is where you're asking before about transmission lines. Okay, so to make interconnections, okay, so to transport signals from one point to another, okay, we need, so always in a circuit, we always need two wires, remember, okay? Okay, because you've got to have, a circuit involves current flowing. So you've got to have, one wire going, one wire coming back, okay? So interconnection, so transporting a signal from, one point to another point on a printed circuit board, between computers, okay, you always need the two wires, okay? So you have, different ways of doing that, just wire pair, twisted pairs, ribbon cables, okay? Coaxial cable, okay, shielded cables. So those are examples of transmission lines, okay? These are more high frequency ones, I think. Yeah, it's mostly coaxial cables, okay? So, so the objective here is to transport some signal with integrity from one point in a circuit to another, okay? And, what models do we need for them? So, we'll look at, so we call those in general, as I said, transmission lines, okay? We need models for them, okay? So on a printed circuit board, you have these transmission lines as well, okay? And it can be different configurations. So, I mean, in the olden days, you didn't have, signals were at very low frequency, okay? And you didn't have these ground and power planes, okay? But, perhaps in that time, the actual frequencies of signals were so slow that, the size of the actual system was small compared to the wavelength. So you get away with it. But nowadays, systems are very fast and they need to be very reliable. So, most printed circuit boards you see nowadays, high-speed systems will always have, at least a ground plane there, okay? And on top of the printed circuit board, you have the wires, okay? And they form a transmission line, so that the wire and the ground plane below form a transmission line, okay? So the signals, electrical signals confined, electric fields are confined to this region, generally around between the two bits of metal, okay, and it propagates along. And you have different configurations. You can have, them looking like this, so maybe two signals there, or something like that. But generally, it's a well-controlled system, okay. So an example of some of these transmission lines here would be this meandering line here. See how it's meandering back and forth? It goes from perhaps one point up here all the way around to some point over here. So why, can anyone let me know why the person has designed the printed circuit board to have such a meandering line like that? What was their objective? What? Increase the impedance? Anyone else? It's due to the delay, okay? So they want to make a delay, okay? So transmission lines have something, so in resistors and other elements that we had in circuit theory so far, had resistors, transistors, capacitors, inductors. they don't have any intrinsic delay, right? The component itself, maybe if you put it in a, LC or RLC network, then perhaps you can say in some sense that, it's got delay, but the actual component itself doesn't have delay, okay? It's just, V equals I R, okay? That's the relationship between the voltage and current at a resistor, right? Something like that. So it's instantaneous, okay? Change the voltage, you change the current. Same with a capacitor, it's, I equals C dV dt, right? So the voltage changes and the current changes, right? Whereas we'll see that a property of a transmission line is that it has delay, okay? Because it's not a dimensionless system anymore. So circuit theory, components, ideal resistors, capacitors, inductors were assumed to be dimensionless, okay? But the actual transmission line has a property called delay.
Is that only because of high frequencies? Like if that one's working at a low frequency?
It wouldn't, yeah, I mean, you could approximate it without delay then because, okay, but this is obviously working at high frequencies and they want to introduce a delay for some particular reason. That's right, it depends. Whether you need to model delay or not depends on the frequency that you're working at as well. That's true. Sufficiently low frequency, delay is so small, and we'll look at what is a small delay soon, next lecture, I suspect. Okay, so we need model. The other thing characteristic that a transmission line has is an impedance, which you mentioned. And that's something else, okay, a characteristic impedance. And it's not something you can just measure with a ohm meter, okay? You actually need to infer it. And when you do the lab, you'll see, delays and impedance and perhaps get an idea of what they mean. So as you mentioned earlier, power systems, okay? What you thought of a transmission line, which is true. This is a transmission line. Now, it's working at low frequencies, but it's a very large size, okay? So it's not just the frequency that's important, it's the relationship between the frequency and the size of the circuit, okay? That's the critical thing, okay? So power systems, when they're going over a large distance of thousands of kilometres, then you probably need to model transmission line aspects of that, okay? And high frequency, you have all this sort of stuff. Okay, so perhaps we stop there, okay? And see you tomorrow, and we'll hopefully finish off the rest of this introduction work, and then next week we can start on the mathematical stuff. Okay. Any questions? Anyone? Thanks for coming, guys.
the